everybody, and welcome to Notes Part 2. All right, and this is, in this set of notes, we're going to talk about what's known as a reaction mechanism. All right, as I mentioned in Notes Part 1, many reactions occur in a series of steps. They don't just occur in one quick step. Some do, but most do not. These series of steps we call a reaction mechanism. Okay, so reaction, again, that's my abbreviation, mechanism. All right, the slowest, okay, of these steps is what is known as the rate determining step. All right, so with this rate determining step, I like to kind of just give a real life example of this. So imagine that, you and a couple of your friends and myself, your teacher, are all on the track team, and we are running as a team. All right. So, and how the team is judged is by the time of when the whole team finishes. Well, who then is going to determine how your team does? Is it going to be you, who's the fastest person on the team, or will it be me, who is the slowest person on the team? And your answer to that should be, yeah, it's going to be the slowest person, because the slowest one is going to be the last to cross that finish line. And it's the same is true for a chemical reaction. The slowest step is what is known as the rate determining step. All right, so now how can you tell what that rate determining step is? You can't just by looking at it. You have to figure this out experimentally. So let's just first look at a mechanism where we know the slow and the fast steps. Someone's already figured this out for us. So here are the two steps to my reaction. What I want us to figure out is what's the overall reaction and what are the intermediates and catalysts, if there are any. All right, so the first thing we're going to do, just like we did with our ozone example in Notes Part 1, is we're going to look to see, is there anything that occurs exactly the same on both sides of the arrow? So Br2, no, there's no Br2 on the right. NO, there's no NO by itself on the right, so no. Br2NO, yep, that's on the right, and it's over here on the left. All right, so boom, boom, okay. So that, because it appears on both sides of the arrow exactly the same, is not going to occur in our overall reaction. So let's write out our overall reaction. What's left over? So I have Br2, all right. Then I have NO and NO. So that's 2NO is going to give us, here we go, BRNO, BRNO, 2BRNO. Okay. Now, great, I have my overall reaction. Do I have any intermediates or catalysts? Remember, I told you that an intermediate, the first place you're going to see it is as a product, because it is made in one step and then it is used up in another. So our Br2NO is our intermediate. Is there a catalyst? Is there anything that we first saw as a reactant on the left side and then finally saw as a product? And the answer to that is no, there are none. So we're just going to leave that blank. Okay, so now let's do a little bit of math with this. Okay, so let's talk a little bit about what's known as rate laws. Okay, all right. The rate of reaction varies directly as the product of the concentrations of the reactants in the slowest step of the reaction. Okay, that's a lot of information, but we're going to walk through this. We describe rate laws by using what are known as rate expressions. These, as I mentioned before, have to be determined experimentally. All right, our goal is to look at data and determine how the concentrations of reactants affect the rate. So let's take a look for just kind of our generic reaction. A plus B is going to give us C. Let me just show you what a rate law would look like for this. Okay, we write the word rate. Then that's equal to a lowercase k, and I'm going to describe what all of these are. Then you're going to put brackets around your first reactant, which is A. that is going to actually be to a certain power. And our job is going to be to figure out what that power is. So we'll say that's at a power of X. Then that's going to be multiplied by the concentration of B. All right, so B in brackets. And B is going to be to a certain power that we have to figure out. So let's take a look, okay? So the rate, how quickly the reaction is going to occur, is going to be equal to lowercase k. Well, what is that? That is what is known as a rate law constant. And it is constant for a specific reaction. So this reaction, A plus B yields C, has its own rate law constant. Now, what are these brackets? When something is put into brackets, what that is that's your concentration in terms of molarity. It's a shortcut that we use in chemistry all of the time, and this semester we're going to be using it a lot. So when you see, all right, a substance in brackets, that means its concentration in molarity. Okay. All right. So this is what a generic rate law looks like. Our job is going to be to look at experimental evidence to figure out what this X and what this Y is going to be, because these tell us the impact that the concentration of each of the reactants is going to have. So let's just jump right in, and we are going to look at example 1. All right, so here we go. What is the rate expression and the value of the rate constant for the following reaction? All right, great. So let's take a look. First thing you want to do is write the rate law. So rate is going to be equal, again, not a lot of thought in this. You're just going to put the K, then you're going to look at your reactants. Okay, so the concentration of H2O2 to a certain power. That's what we're going to have to figure out is what that power is going to be. So I'm just going to leave it as a line to remind us what we need to do. Times the concentration of HI to a certain power. So it's these powers, maybe I'll just box them so we know what we're doing there. It's those powers that we need to figure out. Okay, in order to do this, we must look at this experimental evidence. And I've given you 3 trials, and I've given you the concentrations, okay, of each reactant for each trial, and then I'm telling you the rate. All right, so for this, it is a really good idea to have a calculator ready, all right, because while we can see the numbers often and kind of figure it out in our head, a lot of us like to have that calculator just to make us feel a little bit more comfortable. All right, now, the next thing is you need to look at each reactant alone, by itself, without the other one changing. It doesn't matter which one you look at first. All right, let's just go from left to right. So I want to see the impact of H2O2, okay, on my rate. Well, if I want H2O2, I need to pick 2 trials. Those trials need to have H2O2 changing, but HI should stay constant. All right, I'm going to say that again. I want to see the impact of, this is hydrogen peroxide, H2O2. I need to choose 2 trials. H2O2 changes, but HI stays the same. You can only have one thing changing, right? Only one variable there. So if I'm going to look at my different trials, all right, trial 1 and 2, H2O2 actually doesn't change. So that doesn't help me. Okay. Trials 2 and 3, well, I have both of them changing, so that doesn't help me. What about trial 1 and 3? Well, trials 1 and 3, I'm changing H2O2, but look, HI stays constant. So that's what I'm going to look at. I'm going to first look at trials 1 and 3. All right, so for 1 and 3, HI stays the same. What did I do to H2O2? I went from 0.1 to 0.2, so I doubled it. All right, let's look to see what happened to the rate. And again, feel free if you want to use your calculator and just choose the number that is larger, 0.0152, divide it by the smaller, 0.0076. And yeah, I doubled this concentration and the rate doubled. All right, if that happens, if you double and the rate doubles, the exponent that you give it, and I'm just going to erase my box here, my exponent is going to be a 1. All right, because we know mathematically, if k has to stay the same, if I double this, the rate is going to double. So if you double and the rate doubles, the exponent's going to be 1. Let's now figure it out for HI. So for HI, I need to figure out which two trials to look at. Again, I need HI changing, but H2O2 does not change. So that's going to be trials 1 and 2. That stays constant, HI doubles, and our rate also doubles. So the exponent for HI is also going to be 1. And I'll make those pretty ones so we can see them. Now, just like all of our other ones, typically you don't use a 1, you just leave it because without it being there, it is assumed to be to an exponent of 1. If you want to put it there because it makes you feel like you finished it, that's great, and that's not a problem. All right, so what is the rate expression? Done. And the value of the rate constant. Well, how am I going to solve for this rate constant? This is the easiest part. You have your expression, you have data, choose any trial, and you can solve for k. So it's nice, I can just choose the first one. So my rate is 0.0076 is equal to k. So we're going to solve for that, times 0.1 to the 1 power, times 0.1. All right, and then we just use our nice little calculators. And so we're going to go 0.0076 divided by 0.1 times 0.1. All right, and therefore k is equal to 0.76. All right, so there are my two answers for this one. Okay, so take a look, make sure you have that down. Okay. As far as a label for K, don't worry about that right now. I'm not going to insist that you have one. If you go on to take AP Chemistry next year, you certainly will be dealing with the labels for K. All right, so now let's look at example 2. Okay. If you'd like to try example 2 on your own, that would be great. Okay, so take a moment. All right, so as with all of these, we want to figure out our rate law first. Okay, so my rate is going to be equal to K times the concentration of NO to a certain power times the concentration of Br2 to a certain power. All right, so let's figure out what those powers are going to be. And I apologize, mine's a little altered here as far as how the formatting, but yours should look just fine. So I need to find two trials where Br2 stays the same, but NO changes, and that's trials 2 and 3. All right, so I've doubled NO. What happened to the rate? Well, again, some of us see that right away, but if I don't, I'm gonna take 6.4 divided by 1.6, and what did I get? It went up. So this doubled, right? So this was 2 times, this was 4 times. When this happens, when you double the concentration and you get 4 times, you're going to square that reactant, okay? So you're doubling it and it quadruples, you square. Some students like to think of it as you have 2 here, a 4 here, 4 divided by 2 gives you 2. If that makes you feel comfortable, then great. However, mathematically, you like to think of this, that's perfectly fine. We still have to deal with Br2, so let's do that. Let's find our 2 trials with Br2, and those are going to be trials 1 and 2 because NO stays the same. I have doubled this, and what happened to the rate? The rate doubled. Well, when you double and it doubles, that's just going to get that exponent of 1. And that is your rate law. Okay, calculate the rate constant. Again, just like before, I just usually take the first trial. It doesn't make any difference, but you're going to go 0.8 is your rate, and that's equal to K times 1 squared times 1. All right, so the math here is not exactly too exciting because K then, of course, is going to be 0.8. But that's fine. Had you chosen trial 2 or trial 3, it will still come out to be 0.8, okay? All right, so let's take a look at actually, before we get to our final example, I do want to get you ready for your practice sheet. And just note that we have seen exponents of 1. Remember, you double, it doubles, it gets an exponent of 1. We've seen exponents of 2. If you double and it quadruples, it gets a 2. All right, the last type of situation that you will see is you will change a concentration and you will actually see that the rate does not change at all. All right, and when that happens, it would get an exponent of 0. So let's say concentration of A, if you change that concentration and the rate stays the same, all right, that means that that particular reactant, okay, was not part of your slow step, and it will get an exponent of 0. So if you change the concentration and the rate is the same, okay, you're going to give that an exponent of 0. And that means that it was not part of the slow step. All right, that's how we can look at experimental evidence, and it really gives us a nice idea as to what's going on in our reactions. Okay, so again, you're going to be looking to see whether these exponents are going to be 1, double and double, 2, double quadruple, or 0. You change that concentration and nothing happens to the rate. All right, so let's take a look at our final example. And this is kind of going back to our beginning, okay? And this is if we know the slow step. And once in a while, you will be given a situation like this, all right, where I give you the overall reaction, okay? But then I give you the mechanism as well. I tell you the slow and the fast step. You can actually write the rate law from this. Okay, and you can do this because you know the slow step. So be careful with this. This is something that people kind of fall in love with, but it's only if you know the slow step. If you know the slowest step, you can use the coefficients for the rate order in the expression. How are you going to do that? Well, you're going to look at just this slow step. All right, and in this slow step, I can just directly write the rate law. The rate is equal to K times the concentration of A times the concentration of B. And my exponents are my coefficients, which in this case are both 1. Notice, though, this does not match up to the overall reaction because B has a coefficient of 2 in this overall reaction. So you cannot do this from overall reactions, only if I tell you the slowest step. Okay, great. Let's now also look at, I've written my rate law. Let's go back and make sure we can do our intermediates, all right, and our catalysts, okay? And we're gonna just take a look really quick. Remember, I'm looking for anything that shows up on both the right and the left, okay? So here are my 2 steps, and what do I have that shows up on both the right and the left? All right, so I have C, okay, right here, I produce it, and then I use it up, okay? B's are only on my left, D's and E's are only on my right. So my intermediate is C. Do I have any catalysts? Do I have anything that I started with that I didn't end with? I do not, so catalysts would be none. Okay, great. Final thing, once you have your rate law, any rate law expression, we can figure out what's known as the order of that reaction. Okay, so the order of that reaction is simply the exponents counted up. So looking at a rate law expression, you can give the order for the reaction. So for example, we'll just look back up here. If your rate is equal to K times the concentration of A to the first times the concentration of B to the first, your order for this reaction, this one would be second order, because I just simply added 1 plus 1. You're just adding up those exponents. All right, fantastic. We're going to stop here and we're going to do a lot of practice on this. Have a great day.